And for our last video about improper integrals, this may actually take a little bit longer. We're going to talk about convergence or divergence comparison tests. So sometimes you either don't want to or can't integrate an improper integral with elementary methods, and you might still want to determine whether it converges or not by a simple test. We'll show these tests for type 1 integrals, but they will still hold for type 2. So here is the direct comparison test. If you have continuous functions f and g on a to infinity with f bounded below by 0 and above by g of x. So that's saying it's a positive function. It doesn't really have to be uniquely positive, but this is just making sure it doesn't go to negative infinity past g as well. So bounded above by g. Then the integral of f converges if the integral of g converges, and the integral of g diverges if the integral of f diverges. Let's investigate that a little bit. So if you think about this, g, the function g, bounds f from above. So if g's integral is finite, that means f's integral has to be finite as well because it's bounded by g. We actually had a rule that if functions have this bound, their integrals have to have this bound as well. So if the integral of g is finite, integral of f must be finite. Similarly, if the integral of f is infinite, well, because it bounds g below, g has to be pushed to infinity as well. There's no way for it to be bounded below by an infinite integral and not be infinite itself. So that's what we're doing here with the direct comparison test. Now the hard part is that you have to come up with a function that you know it's convergence or divergent, and you can compare it with the function you're curious about. That's the hard part of the direct comparison test. The limit comparison test is a little bit simpler. It says if you still have to have positive functions and you still have to be continuous. This one, if you take their limit of the functions, not the integrals, the functions over each other, and you get a finite value, then they have to have the same convergence or divergence. So if f converges, so does g. If f diverges, so does g. And vice versa. We're not actually going to prove the comparison test. The proof for the direct comparison test is actually very simple. It just uses Theorem 2 of section 5.3 in our book. It was the property of integrals that said, I think I just referred to it a bit ago, if f of x is less than or equal to g of x, then integral of f of x from a to b is less than or equal to g of x. That actually is all you need, because then if g is finite, this integral is finite, so is this one. If this integral is infinite, so is this one. Super simple proof. Alright, let's do our first example here. This is section 8.8, problem 60 on page 513. So, let's talk about different ways of doing this one. First off, here's a very important comparison you'll use a lot. X is greater than ln of x as x goes to infinity. It's very simple to show this. Just do, say, a quick limit. Limit as x goes to infinity of x over ln of x. If you do L'Hopital's rule, this is limit x goes to infinity of 1 over x, which would be limit as x goes to infinity of x, which just goes to infinity. That means the top must increase more quickly than the bottom. So x is greater than ln of x. Similarly, since they're both positive, you can take 1 over x is actually less than ln of x. as x goes to infinity. And what's nice about it is that both of these have very simple integrals. Integral of x, of course, is 1/2 x squared. Integral of 1 over x is ln of x. And here's actually something else that's very useful. We use these reciprocal functions a lot. If you look at the integral of x to the p from, well, just some finite value to infinity, this is called a p-series integral. And if you think about p, this x to the p will be on the denominator as long as p is greater than 1. If it's 1, you get 1 over x, which is natural log, and you plug in infinity. Looks like a b. Plug in infinity, and ln of infinity still goes to infinity. If you have, 0 on the bottom, it'd just be 1 over 1. Integral will be x. But yeah, anything bigger than 1, so like even 1 over x to the 1.2. Integrate that, the x is still in the denominator, you'd be plugging in the infinity, it would go to 0. So this thing converges for p greater than 1, diverges for p less than or equal to 1. It's a very useful integral to know about. So our text actually talks about this in one of the examples. So in this one, well, it kind of depends on what you think it's going to be. If you think about infinity, ln is going to infinity, ln of infinity. I think it's probably going to infinity. So if we want to bound it below by something, we need to use the 1 over x's. In this case, bounding with like ln of 1 over x wouldn't actually work, because if you do the work for this, because this goes to 0 as x goes to infinity, ln of 0 is negative infinity. So this is actually going to increase more quickly than this. So this is not true. If you do the limit of this over this, you'll see it'll go to 0 because this is actually larger. But if we consider taking this as our lead, 1 over x is less than ln of x, well, maybe it's less than ln of x. Well, let's check. 1 over x. So the limit as x goes to infinity. It doesn't really matter. I'll put the ln's on the top. ln of x over 1 over x. Is this going to be larger than this? I think it will be, because this is going to go to 0 and this is going to go to infinity. Yeah, if you do... Yeah, in fact, it's not even indeterminate, really. Well, I guess it is. No, it's not even really indeterminate. Top's going to infinity, bottom's going to 0. So yeah. So, with that in mind, we're actually just going to bound this with 1 over x. We integrate this from e to the e to infinity. This will be infinite, because if you do integral e to the e to infinity of 1 over x dx, you get, let's see here. What do you get? Ln of x, that's right, ln of x in absolute value, although the absolute value isn't that important. E to the e, and infinity. And of course, ln affinities is going to infinity, so this is divergent. So since this function bounded this function from below, divergent by DCT, direct comparison test. The problem with this one, this is an improper integral of type 2, because you see the bottom's going to infinity. But it's also doing this thing, where it's doing the subtraction. So the question is, will that subtraction cancel out the 0 part of it? Well, let's see here. There's actually a hint in the book. They say the hint is that t is greater than sine t for t greater than or equals 0. That's, I would say, is true in general, yeah. Sine t oscillates, but t will keep increasing. So with that in mind, we could use a direct comparison and say, well, if t is bigger than sine t, then we can say this is less than or equal to, let's see, 1 over t plus t. That is certainly true. No, it'd be greater than. Greater than. Because I made the denominator larger, the whole fraction would be smaller. Yeah, that's right. So that's integral 0 to 1 of 1 over 2t, or 1/2. So that's 1/2 0 to 1 of ln of t. And then that's going to be 1/2 times 0 minus the limit as a goes to 0 from the right of ln of a. This goes to negative infinity. So this diverges, and the original diverges by dct. In this case, though, I think I would just compare it with 1 over t, because sine t isn't going to do much, because sine t only oscillates between -1 and +1. This is a divergent integral. We know that, because, we honestly just did it, more or less. So if we do a limit comparison, dt, let's see, 1 over t minus sine t, and do the limit as t goes to, in this case, it would be 1 is not really the problem. We're really considering 0. Because 1 minus sine of 1 is not a problem. In fact, it's not actually undefined here at all. It's just a 0. Because sine 1 is not 1. I forgot about that. Okay. So, if we consider this, it's indeterminate right now. But if we take derivative... In fact, before we do that, though, let's simplify this algebraically. Derivatives will be a lot simpler. T minus sine t over t. Okie dokie. Now we do L'Hopital's rule, because now we'd be getting 0 over 0, so yeah, it's indeterminate. Limit as t goes to 0 of 1 minus cosine t over 1. But you see here again the difficulty you encounter in doing this, and that I just got an inconclusive case again. This needs to be greater than 0 to be doing it, and I just got 0. I'll get us an integral we can use the limit comparison test on, because I really do want to show that off. Now this problem, if you'll note, has exponential functions on the denominator. Well, the way to think about this is what is going to be kind of the most important factor on the bottom here, because e to the x has a larger base than 2. E is, about 2.7. So this term is going to dominate. So I'm actually going to compare it with 1 over e to the x. I know something about that already, because, if you look at 1 to infinity of 1 over e to the x, that is integral dx. That is integral 1 to infinity of e to the negative x dx, which is just negative 1 over e to the negative 1 over e to the x from 1 to infinity. And that will converge, because if you take the limit as this exponent goes to infinity, this thing goes to 0, so you get 0 plus 1 over e. So that's a convergent integral, and let's compare it with this. So if we do 1 over e to the x minus 2 to the x over 1 over e to the x, this is going to be e to the x over e to the x minus 2 to the x. And if we do a little bit of work here, I can divide top and bottom by e to the x. I get 1 on the top, 1 minus 2 over e to the x. Limit as x goes to infinity. And 2 over e, because that's less than 1, because e is bigger than 2. As you get higher and higher powers, this thing will go to 0, but then you get 1 over 1, so this goes to 1. Because of that, they both have to converge or both diverge. We know this converges. So, converges by LCT, limit comparison test. It's actually a super nice test if you can come up with a decent comparison function. It's probably a little bit easier than the direct comparison. It's just you got to worry about that inconclusive case. So that's where we're going to stop this section. We'll start up chapter 9 next time, because remember, we're not doing 8, 9. It's an interesting section if you want to look at it. It's all about probability doing integration. It's actually kind of ties in a little bit to statistics when you talk about probability density functions, like for the normal distribution and other things. But we're going to go ahead and move on to chapter 9 and revisit differential equations again. So that should be a good time. We'll talk in that video.